Okay, let's say a set S of equations is with the variables x1, x2 to xn is called regular. Okay, let's say R regular if okay, on a set A, if any R coloring of A induces a monochromatic solutions. x1, x2 up to xn in A. So no matter how I color set A, you have a monochromatic solution. So for instance, if S is like the equation, I mean, I don't know whether I can call it set, but let's say S is x1 plus x2 is equal to x3, right? If this is the S, then by Schur's theorem, S is R regular for any R. And we say S is regular if S is R regular for any any positive integer R. Okay, I forgot to say on which set, on the n. So n is the set of positive integers, right? So we've seen a few examples of regular set of equations. So Schur's theorem is 1, so x1 plus x2 is equal to x3. This is regular. And another instance is the Rado's generalization. This equation, this is regular on the set of positive integers. No matter how I color the positive integers. Okay, I mean not that one. But let me say this. So example, x1 plus x2, x no matter like 100 is x101. This is regular. Right? Because there's a monochromatic solution no matter how I color the set of positive integers with binary colors. So the question is, well, the question is how to characterize a regular set of equations. And this is what Rado did in his PhD thesis. The advisor of Rado was Schur. So in this section, we're gonna first deal with the simplest case. So here's the theorem due to Rado. Okay. Wrote S. So let me write S as notation. As a notation, we write this way. So this just means that you have variables from x1 up to xn. Let's say it's a set of a single linear homogeneous equation x1 c1 x1 c2 x2 cn xn is equal to 0. Later we will also discuss the situation where you have a multiple equations, but now for simplicity, now we only focus on this simple case with the integer coefficient c1 c2 Cn.
네. 알겠습니다. 웹에서
Then S is regular if and only if. So what is the conditions? F is regular on and if and only if sum of the Ci is 0 for some non-empty subset of 1 up to n. Okay, is that the theorem? So for instance, x plus y is equal to g. This is the surest theorem. And Rado's theorem says, well, this is regular because when you look at 1 plus minus 1, that's 0. Right? X plus y is equal to twice. This is still fine, right? What about that? That's not regular. So this is a complete characterization. So how do we prove? How do we prove such a theorem? Let me first show you the forward direction. Right? So what I mean is, why do we need such a thing? If it's regular, why do we always have a subset, non-empty subset whose sum of the coefficients, corresponding sum of the coefficients is 0? Okay, so let C1, C2, Cn be fixed integers. And suppose that sum of the partial sum is always non-zero for all non-empty subsets I of 1 up to n. Right? Now what we're going to do is choose a prime p such that this is not non-zero modulo p. Well, we're talking about only finitely many values. The set I, the number n is fixed, right? There are only finitely many values, and therefore, and all of them are non-zero. So I can choose a prime p so that all of them are non-zero modulo p. Choose a prime which is not a divisor of any of the partial sums. Right? Since n is finite, such p exists. Right? Now we are going to define a p minus 1 coloring chi of 1, 2, 3 up to p minus 1 as follows. So if I have some number m, what we're gonna do is, well, m, when I do the factoring, m is gonna be like something like p to the l times a, where a is not divisible by p, right? So this is what l is chosen to be maximum, so that m is equal to p to the l times a, right? In this case, we color this by A. Right? I hope everybody knows this notation. P doesn't divide A. Right? So this is P part and non-P part. So I take away all factors, I mean all P factors, and then the remaining is the oh wait, no, is this what I want? Modular P. Let me, so the remainder. So when so that A, so the color is the remainder in A divided by P. So the color is from 0 to P minus 1, right? Now, we call such a coloring the base P coloring. All right. Now, we claim that there is no monochromatic solution with chi. Suppose that x1, x2, xn is a solution of S with all these things have the same color. Right? Now let L now what you can imagine is for each I, let Li be the maximum integer such that P to the Li divide Xi, right? So then, and let L be the minimum of L1, L2, and Ln. Now what can we observe? I know that Xi right. So if I did Xi divided by P to the Li, this is integer, is equal to the color modulo P, right? So if I divide Xi by P to the L, this is equal to U or 0 modulo P. Because sometimes if L is equal to Li, then it's U, otherwise 0. That is, if Li is bigger, then it's 0. Now let I be the set of indices such that L is equal to Li. Now let's look at the situations. What's going to happen? I know that Ci, Xi, sum of this thing is 0 modulo P. This implies that since well, let's say modulo P to the L, P to the L plus 1, okay, and all of Xi is a multiple of P to the L, so let's divide. So Ci Xi over P to the L, 0 modulo P to P. But I know that this thing is either u or 0. So u is non-zero, right? So this is ci times u, where I is in I. This is 0 modulo p. But u is constant and non-zero. So let me say this way. So p doesn't divide u, so therefore sum of ci is 0 modulo p. But that's contradiction, because we chose p so that any partial sum is non-zero modulo p. All right. So that's the proof for the forward direction. Now let's prove the backward direction. Suppose that x1, x2, xn is a solution of S. So suppose this is a monochromatic solution. Oh, the colors are same. No, is that what we want? No, we want to find the monochromatic solution. So that's not what we want. We want, yeah. So what we want is, yeah. So suppose that C1, C2 up to CK is 0 for some K. By rearranging by permitting names, we can assume that the partial sum from 1 up to k is 0. And also we can assume that ci is non-zero for all I. Because if I have some ci which is 0, then I can ignore that. It has nothing to do with the solution. So let chi be the R coloring. Now our goal is to find the monochromatic solutions. But if C1 plus C2 per CK is equal to yeah, if their sum is equal to n, then we can take no let me see. Oh, okay, let me say not this one. If k is equal to n, then we can take x1, x2, all of them to be equal. Let's say 1. Then 1 plus 1 plus means c1 plus c1, c2 times 1, and cn times 1 is equal to 0 anyway. So it's a monochromatic solution. Therefore, we may assume k is less than n. And we can actually assume choose k maximum. So then we may assume the remaining, so ck plus 1, ck plus 2, this sum is non-zero. Okay? Now let a be the greatest common denominator. I mean, no, greatest common divisor. No, greatest common GCD of C1, C2, CK. And B is the sum and then S be the A over GCD of A and B, still integer, and T be the minus B over GCD of A and B. This is also integer, right? So the goal of this construction is that A times T plus B times S is 0, right? Now, by a theorem in elementary number theory, there are integers, let's say lambda 1, lambda 2, lambda k, such that I can have this linear combination of C1, CK to create any multiple of A, because A is GCD of these numbers, so I can create any multiple. So let me create A times T. Right? This is because A is the GCD of these numbers. Now let xi be the A plus lambda I t if I is from 1 up to k, and otherwise I take SD if I is bigger than k. Now let's look at the CIXI. What is that? Well, from 1 up to k, it's going to be CIA plus lambda I d. From k plus 1 to n, it's going to be S times CI S times d. But the sum... What? Yeah, but sum of CI is 0. So what I get is... So sum of CI times A, which is 0, plus sum of CI lambda I times D, plus, and then here you have ST times B, right? Now, what is that? This is 0, so it's gonna be, and this is AT, so AT D plus BSD, but AT plus BS is 0. So x1, x2, xn is a solution of S. As long as, of course, I need to make sure that these numbers are positive. So I have a lot of freedom to choose, right? So I can choose, I mean, not a lot, but I can choose A and D. Lambdas are fixed, right? Lambdas are given. So lambda S and given, I need to choose A and D so that this is monochromatic. And now some of you may recall that this could be related to something you may have seen. So let me, right? So what remains? Now, let me state the following. Now it's enough to prove the following. Okay. For all KRS, there exists n, which is equal to n of KRS, such that for every R coloring of n, there exists A and D, so that A plus D, A plus 2D, well, let me first write this. It's monochromatic. Why is this enough? Well, the thing is, take A prime as A plus. Okay, what I want is take K prime as twice K, something like twice K. Yeah. Then we're gonna have A plus D. Yeah, with the, let me say with a different parameter. A plus 2D and A plus K 2K minus 1 D and SD. Now then choose some number in the middle. Let's say A prime as A plus KD, right? Then A prime plus any lambda D for any lambda less than or equal to, let's say, K, have the same color, right? And that's how we're gonna set up. So we're gonna set for this lemma. When we apply this lemma, we will choose K to be the twice. We choose this K to be twice the maximum lambda I, right? I mean, bigger than twice, bigger, like maybe twice maximum lambda I plus 1, let's say. And then we apply that lemma, then we find the arithmetic progression together with the property that S times D has the same color. And then you choose the middle one as your A, new A, and then anything you go to the forward direction or backward direction, all of them have the same color. So lambda I, even if lambda I is negative, they will still have the same color, right? So that's the idea. So this lemma is a strengthening of van der Waals theorem. Right? Not only you have this arithmetic progression of length k, but you also have the property that S times D have the same color. Okay. Now, the proof of this lemma is by induction on R. And if you only have one color, then it's trivial. Everybody has same color. So we may assume R is bigger than 1. And I'm going to take N to be something. I will fill in later. Okay. And let chi be an R coloring of 1 up to N. All right. Now, what we're going to do is to so let's say N is S times something. So I will fill in later. Oh, by the way, yeah, okay, never mind. Okay, maybe let me first write the formula. So W of K, so W is this van der Waals number. So we want to find the sequence, arithmetic progression of lengths equal to this when you color by R colors. Okay. Let me write this as van der Waals number. Right. So if I color this first hand integers by R colors, then there exists a monochromatic arithmetic progression let's say A plus ID prime, where I is from 0 to K times N of K R minus 1S. What is this N function? Oh, by the way, this is a function given here, right? So we have something by induction. This is induction R, so when you have R minus 1, such a number exists. That's the assumption. For some A, for some A and D prime in the first integers, right, of this form. All right. Yes. This is by van der Waals theorem. And let's say that color is red. Or 1. Okay, I mean. So if right, if SD prime J is red, monochromatic, say red, for some J, in, let's say, for certain j in n of k r minus 1 s, yes, then let d be equal to d prime j. Now then sd and a plus I d for all I from 0 to this k have the same color. All red, right? Why? Because this is actually a subsequence of that. So everything here was red, so this is red, and this we chose it to be red. So therefore, we may assume that therefore we may assume s times d prime times j is not red for all j here. Now that's interesting. So you have a st prime times 1, st prime times 2, and st prime times n times k r minus 1 s, right? Now let's ignore all others. You map this to 1, you map this to 2, you map this to n k r minus 1 s, right? And then think of the coloring. So let chi prime be a coloring of n of k r minus 1 s such that like chi prime of I is equal to chi of st prime I. Then by induction hypothesis, there are a and d, a prime d prime, such that a prime plus d prime, a prime plus 2d prime, up to a prime plus k minus 1 d prime, and sd prime have the same color under chi prime, right? Because chi prime only has r minus 1 colors. None of them is red. So this implies that now that means sd prime a prime, sd prime a prime plus sd prime d, sd prime a prime plus twice sd prime d, and until sd prime a prime plus k minus 1 s d prime d prime and s d prime s d yes s d prime have the same color under chi. Wait, what's wrong here? What I want to do is take this as my A, right? And then my D is this. This is my D. SD prime D, right? Oh, no, what is D? Oh, I see. So I realize I shouldn't use D prime because D prime was used. All right. So I should say D double prime, let's say. What's the best way to fix it? Let's say D bar. D prime bar. Right? So D prime bar, D prime bar, D prime bar, and D prime bar. So SD prime D prime is D, and SD prime D bar. Okay, that's D. Then SD prime D. Yeah, so this is my D. So that means take A to be SD prime A prime and D be SD prime D prime bar. This work. All right, so that's it. That means no matter how, so this is extension of van der Waals theorem. Not only I can control the arithmetic progression to have same color, but the s times this difference, common difference, is also have the same, that has also same color. And in the proof of Radol's theorem, well, I can choose A as the middle of this arithmetic progression. Then no matter how you go backwards or forward with the same as a multiple of the common difference, you have the same color, and that's exactly how you control the solutions, right? So these lambdas are fixed based on the coefficients, and then there will be some maximum lambda I you need. So how much you go? So take the lambda, you choose k to be long enough, k to be big enough, so that no matter how you go by lambda I step forward or backward, you still have the same color. All right, so that's proof of the Radol's theorem, which is based on van der Waals theorem. So we cannot say so far by using this proof that we have a second proof of van der Waals theorem, because this uses van der Waals theorem. Anyway, that's characterization of regular equations.